This is the third installment of our series, Foundation Models for Embodied Decision-Making Agents. Today I want to talk about Nerfs, Occupancy Networks, and Transformers. These are three types of architectures that try to capture some sort of vision and depth. So it's not just what can a machine see in terms of pixel representation, but it's also where is the thing that it sees, and how fast will it get there, and what is potentially around that that object. So that's kind of what we mean with depth. And for that, I want to go back a little bit in the history of computer vision as it applies to autonomous driving in particular, because for new listeners, Orange Capital Partners is a hedge fund that is invested in fundamentally new concepts, engineering practices with large impact. We have very large positions in what we call real-world AI, in particular Tesla, and we've been working on decision-making agents, embodied decision-making agents now for a while. And that's basically what we mean when we talk about robotics. Think of something that makes decisions, but it's making those decisions in physical space, versus, let's say, a chatbot or Google or something that is making decisions in digital space. So in order to make decisions in physical space, a machine has to see. And I think in the early days of robotics, I think vision was absolutely key. In fact, vision was what robotics was for a while. I mean, if you just take the history of Tesla, robotics was associated with the vision team, which was run by Andrej Karpathy. Karpathy, in the meantime, left, and he went to another place, to OpenAI, to work on Transformers. And I think it's a signal when a leader like that leaves. It's not just because he didn't like the pay package at Tesla. He probably also left because that's where the puck was going. But now let's get back to the history, like I said. So let's start with what enabled computer vision to get on the map. And we start with ImageNet, which is image classification, supervised learning. Fei-Fei Li, Andrej Karpathy, who got his PhD from Fei-Fei Li. We have a whole bunch of people in the Bay Area in particular, but certainly elsewhere too, particularly in Toronto, working on these things. And probably Yann LeCun's convolutional neural nets lead to a really powerful sort of leap forward in computer vision. Convolutional neural nets solve a very particular problem, which is sort of, in a nutshell, they solve the problem or the advantage. They give you the advantage of symmetry. What that means is that if you see something, a computer sees, let's say, a car on a road, and there's nothing else around the car. You don't want to have to constantly recompute every possible position of that image, because the car is the car, and all the stuff around it is kind of all the stuff around it. It doesn't change that much. So convolutional neural nets help you understand that symmetry, in particular when the symmetry breaks, which, this is now a little bit outside of the scope of this episode, but stuff is really when symmetry breaks. So if you're in the desert and you see the horizon, and then there's all of a sudden a car, the symmetry breaks, right? Because you can't. If you just see the horizon, you can go left and right, and it's all the same. And when you see something, that's when going left and right is not the same anymore, and that's what stuff is. So stuff is when symmetry breaks. Convolutional neural nets help understand symmetry, and that's sort of I would say 2015 to 2000, when convolutional neural nets revolutionized robotics, because now we can see stuff with a relatively low compute budget, and self-driving comes along. The autopilot, Tesla, Waymo, and other companies get on the map because they can, of course, because they also have the budget, they have the entrepreneurial spirit and all that, but in particular is also the technology is available, they can do it. Now, the next level is, I would say, a combination of Nerfs and occupancy networks. which are, in my opinion, very similar things. It's just they solve different problems. The nerve side of things, which I'm going to discuss first, is when you're able to take a couple of pictures of an object and reproduce a three-dimensional rendering of that object really well, realistically, and most importantly also with depth. And the reason that works well is because if you look at the actual paper, which I think was published in 2020, Santa Barbara, Berkeley, Google, maybe Stanford, a couple of people from those institutions. What Nerfs, neural radiance fields, do is they are able to take a few pictures and then take into account the position, the angle that the picture was taken from, and then estimate the probability that from those particular angles, if you shoot a ray from that angle towards, a straight ray, you estimate what's the probability that something is there on that line, and then if there is something there, it is able to render what actually is there. In other words, it's able to see whether there is something, and then also what it is, and it does that in form of RGB pixels, and then you can optimize that across a three-dimensional space by taking pictures from different angles, and lo and behold, you have a really good three-dimensional rendering of an object, taking depth into account. This is what Nerfs do, neural radiance fields. The advantage of Nerfs is that they're really good in terms of rendering. The advantage of Nerfs is that they have depth. The disadvantage is they take a long time to train. But the biggest advantage of Nerfs actually would be that once they're trained, they are a really well compressed representation of the world. In other words, you don't need a lot of computer memory to reproduce the rendering. And that's why Nerfs are so useful for video games, for example. So once it's trained, you can send this stuff. In fact, you could almost use the nerve instead of the original. So imagine you take a picture of an apple, which is just a picture of the apple, right? You take 5 pictures of the apple from different sides. You train a nerve that can reproduce a 360-degree rendering of the apple, almost, with 90-something% accuracy. That nerve uses less memory than the 5 pictures you took to train the nerve. Because the neural net that trains the nerve is an unbelievably good representation of the real world. It compresses really well. So it's like everything else in computer vision. It has a lot of fancy names: vision, perception, machine perception. In the end, it's just another way of compression. It's a very smart way to compress, and then there's something called inference, which is a smart way to decompress. That's all there is. So that's what the nerve is. The occupancy network is, I would say, sort of the little cousin of the nerve, because it does a very similar thing. It solves for similar problems. It wants to know where is stuff, but it doesn't really care about the representation. So you could think of an occupancy network as doing the same thing, the density and the positioning and the angle from where you're looking at things, but it doesn't really care about the RGB pixels. So it doesn't really care whether the apple is green, whether the light shines from the top or from the bottom. All an occupancy network does is just needs to know, is there stuff there or not? An occupancy network is also maybe just a fancy word for radar. Think about it that way. Now, the big gorilla in the game, and now we're going back to our history, 2020-ish, Andrej Karpathy leaves Tesla and now joins OpenAI. Why does he do that? It's not just because he didn't like Tesla. It's because transformers are the architecture du jour. And that's just how it is. We can argue about whether that's good or bad and fancy and not fancy. It is what it is. And the reason transformers are architecture du jour is because they generalize extremely well. The self-attention mechanism that was, I think, introduced to the world formally in 2017 with Attention is All You Need paper, this particular mechanism helps the community get to a point of generalization in text space that has been unheard of. And of course, introduces a lot of hype, but also sparks inspiration and hope. Because now we're on track of something that is really interesting, something that can generalize to tasks that it wasn't trained for, and something that can also have a very human-like interaction. We're still in text space, so we're going to get to the robots in a second. We're still in text space. So in text space, we have found a way to generalize to knowledge that hasn't been that knowledge that has not been specifically trained. Of course, the knowledge has to be available somewhere in the memory set, but it can be sort of adjacent. Now let me get to the robot space. Now I want to use a beautiful example from one of the papers I discussed on the Nerfs episodes, and that is the paper that uses, I forgot was it the grounding paper, or maybe no, I think it was offline reinforcement learning for experience. It's a beautiful example. And what it does is the following. It says, look, if you train a robot to go and pick up stuff, you can train a robot to do that, right? You can train a robot to go and pick up stuff. But if you train that robot to go and pick up stuff, and for some reason, the fork that it's supposed to pick up is in a drawer, and you just forgot to train the robot to open the drawer, it won't find it. I mean, it might find it eventually because of stochastic exploration, but it will take a long time. Now, if you do offline reinforcement learning, you could potentially have a whole completely different scenario where somebody opens a drawer. And because of that, when the robot is training itself to pick up stuff, it will have, when it computes the value function in its, in sort of a Q-learning setup, it will compute the next move and have in its value function a non-zero probability that you could have a bit of a higher value if you open a drawer. You might need it, you might not need it. And because of that, it might then, move itself towards a particular drawer, and then lo and behold, actually open the drawer and get that fork. And in other words, it has an experience it was trained with an experience that it can actually use for its benefit. And in that spirit, I think Transformers could, and now we're really in the robot space here. One of the big things that we hope we could achieve as a community is to have multimodal transformers at some point. And what multimodal transformers would do, hopefully, is they would give us the ability to generalize exactly like I just said. The robot could actually get to the point where it could be what we define as a creative machine, which is a machine that can define its own problems. And it can do that because it has an idea of position and rendering and action relative to those positions and renderings, that it has that in its memory space. That's the idea. That's the hope. We're not there yet in terms of, I haven't seen this applied in an engineering set. However, research and papers have spoken about this. We've spoken about this several times in the discussion of Nerfs. So there is absolutely evidence that there is a possibility to apply multimodal transformers to increase the generalization of robots. Last thing I want to say about this is another, I think, big idea that that actually was discussed in the Tesla earnings call. And Musk mentioned it, and it's one of those things when he talks at this point, it's kind of boy cry wolf. We don't even take him seriously anymore, but we should. Because he said something incredibly important. He said that, look, the better we train a model, the less time we need for inference. And this is, this is exactly, let's say, what a Nerf is, right? A Nerf is exactly that, a very well-trained compression of the real world. So the better you do that, the less time you need for inference. You could apply the same thing for a multimodal transformer. And you could actually make the argument here that a multimodal transformer has the ability to represent the real world in a compressed setting, such that the inference becomes a very low budget compute and memory. And this is what it's going to be all about. Let's be clear about this. This is what it's going to be all about. It's going to be about training, of course, but inference and memory for inference will become more and more the bottleneck, particularly when we go to, not just in the self-driving car setting, but let's talk about Optimus here for a second. Let's talk about generalized humanoid robots. They will have to make decisions in real time with very little time for decision making. So meaning, real time, that's what it means. And they will have to make those decisions as accurately as possible. So we can now, I think on a scale, you can look at like, you can not spend too much time training, but then you will have, not a very high accuracy in inference. Or you can flip that around. High budget in training, and then not so much time needed for very accurate inference. And I think that trade-off is something that people don't talk about enough. Musk mentioned it, and I think it's going to become more and more prevalent. It's going to become more and more sort of in people's heads, the idea that you can substitute inference time, inference budget for memory and compute with training. There's a trade-off there. I'm not sure if, I've been interested in some work in theoretical computer science to tackle this problem, to discuss this problem, or to discuss this particular effect a little bit more into detail. But I think this is very, very interesting. And the idea that we have more and more investment in computer memory, in my opinion, is not just about getting better models, but it's also about getting better representations of the real world so that the inference can be done at very low compute and memory budgets, which is crucial for a successful development of robotics. So to summarize, we have three interesting architectures: Nerfs, Occupancy Networks, and Transformers. We believe they all have their application in something, and I think we are big believers in Le Corbusier's comment that a problem well stated offers its own solution. In other words, if we state the problem properly, then we can also figure out which architecture to use. So this is not some guessing game. I think we can do better than that. We can actually have deterministic ideas of what we can use if we define the problem properly. So this is very important. I think occupancy networks are really good for most robotics applications, but I would say Nerfs and Transformers could become more interesting for certain applications where, for example, the setting doesn't change too much, and then you could have a situation where precision and extremely good rendering could actually be more important. Also, let's say haptic sensing could be interesting, like things along those lines. So again, I think each one of these architectures can be applied depending on the application, depending on the problem. And it's great that we have the opportunity to choose amongst these. And I think it's also very interesting to do some further work and understand where exactly the strengths are and the weaknesses, and where the applications can proliferate the field. Thank you.